This video will discuss how to measure effect size for two independent samples. So if the null hypothesis is rejected, the effect size should be determined with a variety of different techniques. First, we'll discuss Cohen's d. Now, Cohen's d, which should look somewhat familiar to what we saw when we were doing a one-sample t-test. So if the null hypothesis is rejected, the effect size should be determined, and one formula to determine effect size is Cohen's d. Now, we saw Cohen's d when we did a one-sample t-test, and it's not much different here. So the estimated d is the estimated mean difference, so your mean 1 minus your mean 2, and your estimated standard deviation. So here we have variance, and so remember the square root of our pooled variance is going to give us our estimated standard deviation. So the formula really isn't any different. So let's take a look at this example. In a study with a sample size of 16 scores in an independent treatment, sample 1 has a mean of 89.5 with a sum of squared deviations of 1,005, and sample 2 has a mean of 82 with a sum of squared deviations of 1,155. The data produce a t-score of 2.5. So we want to know what's Cohen's d for this. So first we need to get our pooled variance, and this is our pooled variance formula. So to get our pooled variance, which remember that S squared is variance and the P stands for the pooled, we're going to take our SS1, which is 1,005, plus our SS2, which is 1,155. I'm going to put that over our degrees of freedom for sample 1 and our degrees of freedom for sample 2. So we had an n of 16 scores in each sample. So that gives us a degrees of freedom of n minus 1, which is 15. So we had 15 in the first treatment, 15 in the second sample, so that gives us 1,160 over 30, which gives us 72. Next, to calculate Cohen's d, Cohen's d is going to be the difference between mean 1 and mean 2, so 89.5 minus 82 over the square root of 72, which is going to give us 7.5 over 8.485, which is going to give us 0.884 if we round up. Now it's your turn. So go back to practice problem set number 1 that you turned in on Monday, and go ahead and look at that number 7, and just let's calculate the d, Cohen's d for that problem. So we knew we had a pooled variance of 56. We calculated that previously. We had an estimated standard error. So the square root, so our S that we need, the square root of 56 is going to be 7.483. So to compute Cohen's d, we take the first mean, subtract the second mean, and we divide that by our S, or the square root of our pooled variance, and that's going to give us a 0.935. Now, yes, technically it's a negative number. However, when we're talking about effect size, we're really only going to be using positive numbers. So now we're going to discuss confidence intervals for the independent measures t-test. So when we're talking about confidence intervals, the difference between the means is used to estimate the population mean difference. So remember, these are the sample means, and they're used to estimate that population mean difference. So the t equation is solved for the unknown population mean difference. So this is the equation that we're looking at. And remember, we're getting a confidence interval for these unknown population means. So for this example, we've seen before, it's about the dimly lit and brightly lit rooms. One study had a mean of 12, and the other one had a mean of 8. The estimated standard error was 1.5. One sample had 8 scores, or 8 scores on each sample, I should say, giving us a degrees of freedom of 14. Because if we have degrees of freedom n minus 1 for one sample, it would be 8 minus 1, or 7. Degrees of freedom in our second sample is n minus 1. So also 8 minus 1, because each sample had an n of 8, also equals 7. So together, gives us 14. And we're using a 95 confidence interval, which means outside of that confidence interval is 5%, or 0.05, in the two tails combined. So we're going to go over here. We have degrees of freedom of 14, 0.05 in the two tails combined, giving us 2.145 as our critical t. Now let's go ahead and use this formula. So we're solving for our unknown means. And when we did the sample previously, we did 8 minus 12 to give us a negative 4. But again, when we're talking about confidence intervals and effect size, it's nicer to stick with positive numbers. So we're going to do plus or minus our t-score that we just found on the table on the previous slide, which was 2.145. And then we also said we knew our estimated standard error was 1.5. So that's just using this formula up here. We put in our standard error, we put in the t from the previous table, we use these numbers to calculate our mean difference. And that's going to give us 4 plus or minus 3.2175. In other words, our confidence interval is going to go from 7.2175 to 0.7825. So that's 4 plus 3.2175 and 4 minus 3.2175 gives us those values. Now, if we put that on a number graph, we're going from a little bit below 0, or a little bit below 1, I should say, sorry, to a little bit above 7. That's our confidence interval. So we're 95% confidence if we were to do this experiment again, pulling the sample from the same populations, we would get a mean that would fall in between those again. And we would get the same t-score that would fall in between those values as well. Now note that it's outside of 0. Because our confidence interval is outside of 0, we reject the null hypothesis. If our confidence interval included 0, we would fail to reject. So if you ever see a confidence interval that has 0 in it, you know immediately that you're failing to reject the null hypothesis. So again, if we fail to reject the null hypothesis, what is the confidence interval going to contain? 0.